Hello, students. Our topic this week is compound probability, the probability of more than one event happening. To understand this, you need to know the difference between independent and dependent events. With independent events, the outcome of one event doesn't affect the probability of the other. For example, you roll a die, you spin a spinner. It doesn't matter what I roll on the die. It's not going to have any effect whatsoever on what I spin on the spinner. So the spinner is independent of the die. Dependent events, the outcome of one event does affect the probability of another. So example, we draw one king from a deck of cards. Well, the probability of drawing a king from a standard 52 card deck is 4 out of 52, or 1 out of 13. The probability of drawing a queen is exactly the same, but the probability of drawing a king and then a queen are dependent events because the probability of drawing a queen, if you've already drawn a king, is different. There are only 51 cards left in the deck. So the probability of drawing a queen is 4 out of 51, not 4 out of 52. And if we were to draw a queen and then a queen, there are only 3 queens left, 51 cards, it would be 3 out of 51. So the probability of drawing a queen depends on what's happened to that deck before you go to draw the queen. So those are dependent events. You also need to know the idea of mutually exclusive events. With mutually exclusive events, you have two events that can't both happen at the same time. For example, if you roll one die, you can't roll both a 5 and an even number. 5's not an even number. So those are mutually exclusive. You can roll a 5 or you can roll an even number, but you can't do both at the same time. So the probability of rolling a 5 and the probability of rolling an even number are mutually exclusive. These next few problems involve independent events because they draw a card, but then they put it back. The assumption is that if you've put it back, you've reshuffled the deck, you have just as much chance of getting that card as any other one. So the first one here, find the probability of drawing a 2 of hearts on the first draw. Well, there's only one 2 of hearts, so the probability of that would be 1 out of 52. And then replacing it, drawing a diamond on the second draw. There are 4 suits, one of them is diamonds, so this would be 1 out of 4. So your answer would be 1 out of 52 times 1 out of 4. When you have independent events, you can actually multiply the two probabilities to get the probability of the compound event. So in this case, you'd have 1 out of 208. Number 2, find the probability of drawing a red face card on the first draw. Well, the probability of drawing a red face card, there are Jack, Queen, King, 3 face cards in each suit. There are 2 suits to the red, so there's 6 out of 52, which you could simplify if you want, but 6 out of 52. And then drawing a black card. Well, half the cards are black. So you would have 6 out of 52 times 1/2. So 3 out of 52 would be your probability. So when you have independent events, you can find the probability of the first one, find the probability of the second, multiply those two probabilities. That's your compound probability. Now let's look at those same two problems, but let's assume we didn't replace the card. If we don't replace the card, there's going to be one less card in the deck. So there'll only be 51 cards to choose from. So the first problem, find the probability of drawing a 2 of hearts on the first draw. Well, there's only one 2 of hearts, so that's 1 out of 52. Then we don't put it back. The probability of drawing a diamond. Well, there are 13 diamonds, and normally the probability of drawing a diamond would be 1 out of 4. But there aren't 52 cards left, there are only 51. So the probability of drawing a diamond is now 13 out of 51. So then you'd have to multiply those two probabilities, and you get 13 over whatever 52 times 51 is. So it gets a bit more complicated. Your probabilities are going to be a little bit off from what you might think they are. But use a calculator. You won't have any problem with these. Number 2, find the probability of drawing a red face card on the first draw. Red face card is 6 out of 52 or 3 out of 26. Okay, so 3 out of 26. And then not putting it back, drawing a black card on the second draw. Well, probability of drawing a black card on the second draw would have been 1/2. Half the cards in the deck are black, but that's not true anymore. More than half of the cards in the deck are black now, 13 out of 51. So you'd have to get that 13 out of 51 and multiply that by 3 out of 26. And you'd end up with 39 over whatever 26 times 51 is. Okay, so the hard part is just figuring out, is this independent or dependent? And what's the conditional probability of that second term? That just means what's the probability given that the first thing happened? Okay, once you find those two probabilities, again, you just multiply them. Okay, a box contains 6 orange marbles, 10 red marbles, 7 purple marbles. So if you pick 2 without looking, what's the probability that both will be red? Well, to start with, we have 10 red marbles. We also have 6 orange and 7 purple. So if we add those all together, we've got 6 plus 10, 16, 23 marbles. So the probability of the first one we pick being red is 10 out of 23. The probability of the next one being red is 9, because we already took out 1 red marble, out of 22, because we took out a marble. So again, this is where you have to look at these as dependent events, and you say the probability of the second one is going to change based on what we got the first time. And number 2, Amber tossed a die onto a black and red checkerboard. What's the probability it will land with a value of 1 on a black square? Well, the probability of the die ending up in 1 is 1 out of 6. The probability of it ending up on a black square is 1 out of 2. It doesn't matter whether it's a 1. There's still only 2 colors on the board, and each of them happens half the time. So these are independent events. So we just multiply those two probabilities. 1/6 times 1/2 would be 1/12. So it's important to know whether these are dependent, as they are in number 1, or independent events, as they are in problem 2. In problem 3 here, Andrea wrote a computer program that generates 2 random numbers between 1 and 9. When she runs it, what's the probability that both values will be more than 5? Well, first of all, are these dependent or independent events? Does the computer care what it generated for the first number when it goes to calculate the second one? Probably not. So these would be independent. So we just have to find each of the probabilities and multiply them. There are 9 numbers here from 1 to 9 that are possibilities. There are 6, 7, 8, and 9 that are greater than 5, right? We don't want to include 5. So there are 4 out of 9 times 4 out of 9 would be 16 out of 81 as our total probability. In number 4, a bowl of fruit is on the table. It contains 4 apples, 6 oranges, and 5 bananas. Brandon and Jason come home from school and randomly grab 1 fruit each. What's the probability that both grab oranges? Well, are these dependent or independent events? If Brandon's quicker, he's going to grab what he wants. He's not going to put it back. So that's gone, right? If he wanted an orange, he grabbed it. Okay? So these are dependent events. The number of oranges left depends on Brandon getting there first. Okay? So because these are dependent events, the first probability is that there are 6 out of 15 fruits. The next probability is 5 out of 14 fruits. So we'd have to multiply those two probabilities to find the compound probability.